In this video, we'll talk about indexing and more specifically about hierarchical indexing. Indexing is a very powerful feature of pandas. When data is indexed properly, it allows us to perform selection and sorting operations much more easily, and it also allows us to access the data in a more convenient and a more powerful way. Very often the data doesn't come with a natural index. In this case, it's up to us to create the index, and it's up to us to create the index in a way that facilitates working with this data. Let's start by looking at this example here. In this example, I have a data frame that has three columns: the state, the year, and then the population. Let's take a look at this question here. Select records pertaining to the state of California. Since state here is a column, the index is the default index going from 0 to length -1, I need to create a mask. Basically, I need to pull my series, state, and compare it to California. This will give me a mask. And then I use the mask to index the data frame, and I get the subset of the data that pertains to California. Now, I had to do this because the state itself is a column, right? The index itself is a bunch of numbers. The same operation could have been conducted much more easily if the index was the state, because I can simply just index and pull the state that I need. Indeed, we can change the index for data frame. That's what the function setIndex does. It basically sets the index to be the column that we provide here. Let's create another data frame, population df2, by converting population df, setting the index to be state. Now, the function setIndex doesn't change the underlying data frame. It returns a new data frame. Hence, what I have done here, I basically assigned it to a new data frame called popdf2. Popdf2 state is no longer a column, state is an index. We can actually double check that. We can call popdf2.index, and that basically will tell us that the index is the state. In contrast, popdf has the range index that goes from 0 to length -1. Now the question is much easy to answer because I can simply ask it to index at position California, log California, and I get what I'm looking for. Moreover, this operation is much more faster than the operation of masking. To gauge the speed of the operation, there is a built-in magic in the notebook called time it. Basically, it runs the operation under question thousands of times and report the average. So this will go on for thousands of loops, thousands of times, and it will give us the average runtime, which is in this case happens to be 121 microseconds plus minus 3.6 microseconds. Okay, let's do the same with the masking here. I'm going to time it. So it will take a while. It will basically run 1,000 loops, and you can see that the average is 362 microseconds. So three more kind of times less efficient to do masking compared to doing indexing. So when we do indexing, we do it for two reasons. One of them is to facilitate operating on the data frame. If one of the operations that we want to do is to select based on the state, then it makes sense to make the index to be the state. Second, we make it to make the operations more efficient. And this efficiency will not manifest itself in a data frame as small as this one. It only becomes important when we have large data frames. Now, if we want to convert a data frame which is indexed to a data frame that doesn't have that has the default index, we can use the function resetIndex. This function, as the name implies, will reset the index. It will move the index to be a column, back again in this case, and it will give us the default index going from 0 to 6. That's a handy function, and you can see it also returns a data frame, and we can stack these operations together. Say I want to index by year, I can do setIndexYear. that will basically set the index to be year. So if I want observations about year, for instance, 2000, I can do 2000 here, basically a string, and I get the observations. Sorry, it's a locked string. I get the observations in year 2000. Okay, let's take a look at this question now. What's the population of California in year 2000? If we have the original data frame, we need to mask because both year and state are columns. So we need to create a composite mask. Year equals to 2000 and state equals to California and the AND operation in between. And then we index using the mask and we get the answer. Now, if I was interested in just the value, then I need to take my data frame and pull this value. So I did log 0 population. Now, in the next data frame, df2, I don't need the mask on the state because the state itself is on the index. So I can use lock here. What I need though, I need a mask on the year because I only need to select those that have a year equals to 2000. And that's what I have done here. So it's a combination of indexing as well as masking in population df2. Let's say pulling data about populations in a certain state year combination is what I need to do the most in this data frame. In this case, it makes sense to make my index to be both state and year, which is actually possible in pandas, and this is what we call a hierarchical index. So you can think about a hierarchical index as a combination of two columns. All of the values that these two columns combine will be one index. Let's take a look. I'm going to set index to be state and year, and let's take a look at my new data frame. In my new data frame, I only have one column, but my index, if I like to take a look at it, it's a multi-index, and each value in the index is a combination of a state and a year, state and a year. So with this new data frame, if I want to pull a certain state, I can do lock California, and that will get the population associated with that state. If I want to get a combination of a state and a year, I can provide lock and provide a tuple, California and the year, and I get that. An intuitive way to do this is to do the lock and then provide the location on the index, which is to get all values of the first level, the state, and one value of the year, which is 2010. Unfortunately, this syntax is not correct. The issue here is that the bracket operator is an operator in Python that it enables to overload. It's basically a function to index. And what we're passing is we're passing values to that functions. Now, when we have a tuple here, this is not something we can overload. So when we do a tuple and then a column, this is just an invalid syntax. Now, one way to overcome this is to do, if I want to get all of the states associated with a year, is basically to do the indexing in the other way around. I can index starting from the year and then going to the state. That basically give me the year and the state in the multi-level index. And then simply speaking, for to get the values associated with 2010, I can do lock and then 2010. That's basically the populations of the states in 2010. That doesn't solve the problem if I want to get all of the years for a certain state. So the solution to this problem is to basically use an internal object in pandas called an index slice. It's basically a powerful way to create a slice, and we can use it with a multi-index. So we just import this object from pandas, and then we tell pandas, like, in this data frame, it has a multi-index as another dimension in the data frame. We basically have a row index which contains two levels, and we can access these two levels independently, the state and the year. And obviously we have the second level, which is with a second axis, which is the column axis. Indeed, it's possible now to do the same operations we do in indexing on the multi-index. So for instance, let's say I just want New York and Texas. I can do a fancy indexing here. I can say, okay, give me Texas, give me New York in year 2010, and all of the columns here, and this is what we get. Okay, it's possible to do slicing now. So I can tell it, well, give me the slice. I mean, it's not very useful here because I only have two values, 2000 to 2010, and I can write, a slice here. Similarly, this one, I mean, it's a column index. We only have one column here, but it's possible to do all of the operations we know about. If I want to select one value, I'm going to get a series here, and the series has the same multi-index, and so on and so forth. So if I had multiple columns, I could have done fancy indexing and slicing as well. So the multi-index is basically converting our two-dimensional data structure, the data frame, to a multi-dimensional one. Effectively, you can think about this data frame as having 3 dimensions, and the third dimension is, so state here, and the third dimension is population. And you can provide the coordinate on each one of these dimensions, the axis, independently. Now, because the data frame itself is kind of like a spreadsheet, it's kind of limited to be 2-dimensional, but each one of these dimensions can have multiple levels, and thus conceptually it can be thought about as a multi-dimensional data structure. We can also have multi-indices on the 2 axes. And this example, I'm just doing it on the column axis. And the book provides a nice example in which we have a multi-index on both axes. So you can have a multi-index on the column axis and a multi-index on the row axis. Let's now talk more about using multi-indexing to embed different dimensions in the data frame. Let's start with the same example, and in this example I'm just adding a new column to the data frame, which is the number of people under 18 in each one of the state in each year. Next, I'm creating a series which has the values under 18 divided over population. That's simply speaking the percentage of people under 18 in each state and each year. Because population DF3 under 18 is a series, and population DF3 population is a series, Pandas is going to align the indices. And of course the index here is a multi-index, but that is not a limitation. It can still align a multi-index, and what we get here is a series that has the same multi-index, and the corresponding operation has been broadcasted to the values. So that's the percentage or the ratio of people under 18 in each one of these states. Now this is a series, and this series is a unidimensional data structure. It's a sequence of values, but each one of these values is indexed on 2 levels, the state and the year. So if you think about the index of your series, this index itself is 2-dimensional. A very useful operation to unpack the dimension on the index is to convert it to be an axis on the series itself. This operation is called unstacking. What it does, it takes a multi-level index, a hierarchical index, and uses one of the axes, in this case the axis that we don't have, which is the columns, to represent the index. So if I unstack my series here, let's actually run the series, is going to take the second level on the multi-index and make it the column axis. So the series, which is a unidimensional data structure, has been converted to a data frame, which is a 2-dimensional data structure here. There may be situations when we want to have a series, a vector, and situations when we want to have a data frame. Like for instance, let's say I want the total average of people under 18. In a series, if I do the mean, it's going to run the mean over all of the values, and I'm going to get the whole mean. However, if I have a data frame and I run the mean, and an aggregate function is going to give me the mean in year 2000 and in year 2010. So that's one of the benefits of stacking or unstacking my data to a, from a series to a data frame and vice versa. I can also unstack, and when I unstack, I can decide which level in my index I want to unstack. By default, it's going to go to the lowest level, which is here, the second level in my multi-index. But I can unstack state, and you can see here, state, which has been a level on my multi-index, has been converted to the axis in this data frame. The opposite operation is called stacking. Stacking takes an axis, the column axis, the second axis, and convert it to be a sublevel on the other axis, on the row index, in the row axis in this case. So if I have a data frame, which is a two-dimensional data structure, simply stacking it will basically convert it to a series. Now, one of the common applications of stacking and unstacking, as I said, is to calculate aggregations. And this is because Pandas in default runs aggregations row-wise, so it operates on the column axis. So I can benefit from this default behavior and say, for instance, I want the grand mean, I can run the mean on a series. But if I want to have the mean over the state, I can unstack my series, making the multi-index, the state level an axis, a column axis in this data frame, and I can do the mean, and this will give me the average value of population under 18 in each one of the state. And similarly, I can unstack here and do the average over a year. So stacking and unstacking are very powerful operations. They may seem confusing in the beginning. Don't confuse this one with transposing. Transposing simply swaps the axis with the columns, the rows with the columns axis. Unstacking creates a new axis where it doesn't exist in the first hand. If you take a look at a series, it doesn't have a column axis, it only has a row axis. When you unstack a multi-index such as this one, it's going to create a new dimension, which is this column axis, thus converting the series to a data frame. Similarly, stacking a data frame is going to compress and it will remove the second axis, which is the column axis, and embed it as a second dimension in the row axis. It reduces it kind of reduces the data frame to a series. We will get back to these operations when we talk about aggregations and also when we talk about converting our data from long to short formats.